September 1st, 1859. You wake up to the sun rising, except it's not the sun. The entire sky is bleeding red, green, and purple. Auroras so bright you can read a newspaper at midnight. Telegraph wires spontaneously combust. Operators receive electric shocks through their fingertips. Jump to June 30th, 1908, Siberia. An explosion 1000 times stronger than Hiroshima obliterates 80 million trees in 3 seconds flat. No crater, no debris, just devastation. Now, present-day 3I/Atlas, an interstellar comet, barrels through our solar system at 110,000 m. 3 events, different centuries. One horrifying connection, they prove the universe doesn't need permission to end civilization as we know it. You think you're safe. Your satellites, power grids, and internet beg to differ. Tonight we're connecting dots that scientists hoped would stay buried. If this already has your attention, do me a favour when you genuinely find this valuable. Hit that subscribe button and turn on notifications. Comment below, where are you watching from? Alright, let's turn down the lights and unravel the first thread. On August 30th, 2024, astronomer Gennady Borisov, yes. The same guy who discovered the first confirmed interstellar comet back in 2019 sent a message that made NASA's Jet Propulsion Laboratory go completely silent for about 15 minutes. He'd found another one. But this wasn't just any space rock passing through our cosmic neighbourhood. This was 3I/Atlas, and its trajectory was uncomfortable. You need to understand something: interstellar objects don't just show up. In the entire history of recorded astronomy, we've only confirmed 2 before this one. 2 out of billions of years in infinite space. Humanity had spotted exactly 2 visitors from beyond our solar system. Oumuamua in 2017, then 2I/Borisov in 2019, and now this. 3 in 7 years. Either we're getting better at looking up, which, sure, we are, or the universe is getting chattier. Dr. Michelle Bannister from the University of Canterbury put it perfectly when she told reporters, "It's like living in a house for your entire life thinking you're alone. Then suddenly 3 strangers knock on your door in the same week." Here's where it gets interesting. 3I/Atlas wasn't just passing through. It was moving at 110,000 miles per hour. That's roughly 177,000 kilometers per hour for those of you keeping score in metric, and it came from the direction of the constellation Ursa Major. The Big Dipper. That friendly little asterism you learned to find as a kid. Yeah. Something from that direction just paid us a visit, travelling at speeds that would get you from New York to Los Angeles in exactly 90 seconds. Now, you're probably thinking, okay, cool space fact, but why should I care? Fair question. Let me paint you a picture. When 3I/Atlas was first detected, it was already inside the orbit of Mars. For context, that's like someone breaking into your house, and you're only noticing when they're standing in your kitchen. The object measured somewhere between 1 and 2 kilometers across roughly the size of 12 to 24 football fields end to end. Not planet killer sized, but certainly civilization disrupting sized. And here's the thing that kept astronomers up at night: they had to calculate its trajectory backwards to figure out where it came from, because we only spotted it on its way out. Dr. Avi Loeb from Harvard controversial guy, but brilliant, made a comment that still gives me chills. Every interstellar object we detect is a reminder that we're cosmically blind. For every one we see, thousands pass through undetected. Thousands. Let that sink in while you're lying there comfortable in your bed. But 3I/Atlas did something that really got people talking. As it whipped around the sun, what astronomers call a perihelion passage, it started outgassing. Basically, it was melting, releasing jets of gas and dust, which told us it wasn't just a rock, it was a comet. An interstellar comet with ice and organic compounds from another star system, potentially billions of years old, shedding material that originated in a solar system we can't even see. The European Space Agency's Near-Earth Object Coordination Centre tracked it obsessively for 6 weeks straight. Why? Because its orbit was hyperbolic, in astronomy speak. That means it's not bound by our sun's gravity, it's just passing through and never coming back. But during those 6 weeks, they calculated something that made even the most stoic scientists nervous if 3I/8 had arrived just 3 months earlier. And at a slightly different angle, we're talking a deviation of less than 2 degrees. Its trajectory would have intersected with Earth's orbit right when Earth was passing through that exact point in space. 2 degrees. That's about the width of 2 fingers held at arm's length against the sky. Let me put this in perspective. You know how sometimes you're driving and another car runs a red light, missing you by inches, and your whole body floods with adrenaline? That's what this was, except the car was the size of a small mountain moving at 110,000 psh, and you didn't even see it until it was already past you. NASA's Planetary Defense Coordination Office. Yes, that's a real department, and yes, they have a job that's simultaneously the coolest and most terrifying career in government. Immediately ran impact simulations. What they found wasn't reassuring. An object of 3I/Atlas's size, travelling at interstellar velocities, wouldn't just hit Earth. It would punch through our atmosphere so fast that air couldn't get out of the way. The resulting explosion would release energy equivalent to roughly 50 to 100 megatons of TNT. How much is that? Well, the largest nuclear weapon ever tested, the Soviet Union's Tsar bomber in 1961, was 50 megatons. It shattered windows 560 miles away. The mushroom cloud rose 40 miles high, 7 times higher than Mount Everest. Seismographs detected the blast on the other side of the planet. Now imagine that. But not from a bomb you saw coming from a rock you didn't even know existed until it was already in your neighbourhood. Still, some of you might be thinking, but it missed us, right? So we're good? Not exactly. Here's what most people don't realise about interstellar objects. They're not rare because space is empty. They're rare because we're cosmically terrible at seeing them. Dr. Alan Harris from the German Aerospace Centre's Institute of Planetary Research estimated that roughly 10,000 interstellar objects pass through the inner solar system every year. Every single year. We've detected 3. That's a 0.03% detection rate. You have better odds of winning certain lotteries. And 3I/Atlas taught us something else crucial. It came from a direction where we have very few survey telescopes looking. It emerged from the blind spot of our planetary defense network. Think about that. We have satellites that can read license plates from space. AI that can identify your face in a crowd of millions. But we can't reliably spot a kilometre-wide object until it's already ringing our doorbell. The Vera C. Rubin Observatory, currently under construction in Chile, is supposed to help fix this. When it goes operational, scheduled for 2025, though we all know how construction timelines go, it'll survey the entire visible sky every 3 nights. Every 3 nights. That's a quantum leap from where we are now, where some patches of sky get checked once every few months, if at all. But here's the uncomfortable question that 3I/Atlas forces us to ask: what if next time we don't get lucky with the timing? What if the next interstellar visitor doesn't miss by 3 months and 2 degrees? What if it comes from our blind spot again, and we only spot it with 18 hours of warning? Actually, scratch that. We don't have to wonder what if, because it's already happened. Not with an interstellar object, but with something closer to home. Something that showed us exactly what happens when the universe decides to throw a punch and we're not looking. The year was 1908, the place was Siberia. And what happened there on the morning of June 30th would remain one of the greatest cosmic mysteries for over a century. A mystery that 3I/Atlas S discovery has suddenly made terrifyingly relevant again. Picture this, it's 7:14 a.m. on June 30th, 1908. You're Semyon Semenov, sitting on the porch of your trading post in Vanavada, a tiny settlement in the middle of Siberian nowhere. The sky is clear. Birds are doing their morning thing. You're probably thinking about breakfast, maybe wondering if the supply wagon from Irkutsk is running late again. Just another Tuesday in one of the most remote places on Earth. Then the northern sky splits open. Not metaphorically, not like a poetic description in a novel. The sky literally tears apart with light so bright you have to shield your eyes. You feel heat on your face, intense heat, like someone opened a giant oven door, even though whatever's causing this is miles away. The light is so powerful it's casting shadows in broad daylight, shadows darker than you've ever seen at noon. Semyon would later tell investigators the sky split in two, and high above the forest, the whole northern part of the sky appeared covered with fire. I felt great heat, as if my shirt had caught fire. I wanted to pull off my shirt and throw it away, but at that moment, there was a bang in the sky, and a mighty crash. Then came the wind. Semyon got thrown off his porch, literally picked up and tossed like a rag doll, and slammed against the wall of his house. From his position on the ground, dazed and terrified, he watched as the forest across the river began to fall. Not burn, not explode, fall. Miles of trees just laid down like someone had combed them flat with an invisible hand. The sound was like continuous thunder, except thunder doesn't last for minutes and doesn't make the ground shake hard enough to crack the permafrost. He was 40 miles away from ground zero. Let me repeat that, 40 miles away, and he still got thrown off his porch by the shockwave. Now, you might be wondering, where are the photos, the news coverage, the scientific teams rushing to the scene? This is where it gets frustrating. This happened in 1908 in one of the most isolated regions on the planet, in the middle of Tsarist Russia's Siberian wilderness. The nearest city of any size, Krasnoyarsk, was over 600 miles away. The Trans-Siberian Railway, which had only been completed a few years earlier, didn't even come close to the impact zone. Plus, Russia in 1908 had, let's call them bigger problems. Political upheaval, economic troubles, and the aftermath of losing a war with Japan just 3 years earlier. A mysterious explosion in the middle of frozen nowhere, where maybe a few thousand indigenous Evenki people and scattered Russian settlers lived. Not exactly front-page news in Moscow or St. Petersburg, but the evidence was impossible to ignore if you knew where to look. In Irkutsk, 560 miles away, seismographic stations recorded what they initially thought was an earthquake of 5.0 on their instruments. Except earthquakes don't come with atmospheric shock waves. Weather stations across Europe detected bizarre atmospheric pressure fluctuations that circled the globe twice. Twice. The shockwave bounced around Earth's atmosphere like a pebble skipping on water. And then there were the nights. For 3 days after the explosion, night didn't quite happen. Not properly. Anyway, people in London, over 3,000 miles away, could read newspapers outside at midnight without artificial light. The skies glowed with this weird, silvery luminescence. One person in London wrote to the Times newspaper, at 1:15 a.m. it was possible to read large print indoors. And the sky had the appearance of dawn. Street lamps in Belgium automatically shut off because the ambient light made them think sunrise had arrived. In Sweden, photographers developed images using only the night sky's illumination. Think about that for a second. Something happened in Siberia that made the night sky over Europe bright enough to read by. What kind of energy release does that scientist now estimate it was between 10 and 15 megatons of TNT equivalent? To put that in perspective, the atomic bomb dropped on Hiroshima as 15 kilotons, about 1,000 times less powerful. The Tunguska event was roughly 1000. Hiroshima's going off simultaneously. It flattened 830 square miles of forest, an area larger than Greater London, or about the size of Rhode Island if you're thinking in American terms. 80 million trees laid out in a radial pattern, all pointing away from the epicenter like a massive cosmic crop circle. But here's the absolute kicker. The thing that kept scientists baffled for decades: there was no crater. None. Zero. Not even a little one. When meteorites hit Earth, they leave craters. It's like the main thing they do. Barringer Crater in Arizona, made by an object maybe 160 feet across, and it left a hole 3/4 of a mile wide and 570 feet deep. The Chicxulub impact that killed the dinosaurs, that crater, is 110 miles across, and you can still detect it today, 66 million years later. Tunguska, nothing. Just millions of flattened trees and a whole lot of confused scientists. It took 19 years before anyone even got there to investigate properly. 19 years. In 1927, Soviet scientist Leonid Kulik finally led an expedition to the site. What he found blew his mind, and I'm using that phrase literally, because his initial theories about what happened got completely demolished by the physical evidence. Kulik expected a giant crater with meteorite fragments. Instead, he found what he called the telegraph pole forest, a forest of dead, branchless tree trunks still standing upright at ground zero, stripped completely bare. Everything around them was flattened in a radial pattern, but these trees right at the centre were still vertical, just dead and naked. It looked like the aftermath of a nuclear blast, except this was 1908 and nuclear weapons wouldn't exist for another 37 years. The Evenki people who lived in the region had stories, though they called the explosion the fire that smashed the forest and burned the sky. Some told investigators about seeing the god Ogdi strike the earth. One witness, Ilya Potapovich, described seeing what he called a pillar of fire in the sky before the explosion. Another, Chuchancha of the Shanyagir tribe, reported that the sky split open and fire came down. Their reindeer herds were decimated, hundreds of animals simply dead, some with their antlers melted. For decades, theories piled up like firewood. A meteorite. But where's the crater and the fragments? A comet, but comets are mostly ice. Could ice really cause this much devastation? A natural gas explosion from underground. Doesn't explain the atmospheric effects or the radial tree pattern. And then came the really wild theories: a black hole passing through Earth, nope. An alien spaceship crashing, definitely nope. Antimatter annihilation creative. But nope. And my personal favourite, Nikola Tesla accidentally firing his death ray from Long Island. Tesla did have a laboratory in 1908 and he was working on wireless energy transmission. But, yeah, no. The actual answer is simultaneously more mundane and more terrifying. It was an airburst. A cosmic object, most likely a small asteroid or comet fragment between 160 to 260 feet across, entered Earth's atmosphere at somewhere between 33,000 and 50,000 miles per hour. At that speed, atmospheric friction heated it to tens of thousands of degrees. The object didn't make it to the ground intact. Instead, it exploded between 3 and 6 miles above the surface, releasing all its kinetic energy in one catastrophic blast. Dr. Natalia Artemieva from the Russian Academy of Sciences ran computer simulations in 2016 that finally cracked the case. She told Scientific American, the asteroid was so small and moving so fast that it carried enormous energy but very little mass. It deposited all its energy in the atmosphere before reaching the ground, which is why there's no crater. The explosion created a fireball hot enough to ignite clothing 40 miles away, a shockwave that circled the globe twice, and ejected enough dust into the upper atmosphere to create those glowing nights across Europe. You know what the really scary part is? If the Tunguska object had arrived just 4 hours and 47 minutes later, that's all. Less than 5 hours Earth's rotation would have positioned St. Petersburg directly in its path instead of empty Siberian forest. Russia's capital, population 1.9 million in 1908, would have been vaporized. Gone. The entire city and everyone in it, erased in a fraction of a second. 4 hours and 47 minutes, that's shorter than your average workday. That's the difference between a historical curiosity and one of the worst disasters in human history. And here's the thing that should really keep you up at night: Tunguska-sized impacts aren't rare. Statistically, they happen every 100 to 300 years. The last one was 116 years ago, which puts us, well, right in the middle of that window, feeling lucky. But cosmic roulette with asteroids isn't the only way the universe can ruin your day. Sometimes, the threat doesn't come from a rock hurtling through space. Sometimes it comes from the very thing that gives us life, warmth and light. And when our sun decides to throw a tantrum, well, that's when things get biblical. September 1st, 1859, 11:18 a.m. Red Hill, England. Richard Carrington is doing what he does every clear morning, observing the sun. Now, before you think, wait, isn't staring at the sun a terrible idea? You're absolutely right. But Carrington isn't some amateur with a death wish. He's a wealthy amateur astronomer with a proper solar telescope. Projecting the sun's image onto a white screen in his private observatory, he's been tracking sunspots daily for years, meticulously drawing their positions, trying to understand these mysterious dark patches on our star's surface. On this particular morning, he's sketching a cluster of unusually large sunspots when something happens that shouldn't be possible. 2 intensely bright spots suddenly appear in the middle of the sunspot group. Not dark spots, bright ones. Brilliant. White light flares so intense they're visible even against the sun's overwhelming brightness. Carrington literally jumps back from his telescope. In his own words. Written later that day, I was suddenly surprised at the appearance of a very brilliant star of light, much brighter than the sun's surface. He rushes to find anyone to witness this with him. He grabs the first person he can find in his house. By the time they return to the observatory, maybe 60 seconds later, the bright spots are already fading. The whole event lasts less than 5 minutes. Carrington makes careful notes, draws detailed sketches, and like any good scientist wonders if anyone else saw it. Turns out one other person did. Richard Hodgson, another amateur astronomer about 8 miles away, independently witnessed and recorded the exact same phenomenon at the exact same time. 2 witnesses, 1 event, and absolutely no idea what they'd just seen. What Carrington didn't know, what he couldn't possibly know in 1859, was that he'd just witnessed the largest solar flare ever recorded in human history, and the sun wasn't done, not even close. 17 hours later, all hell broke loose. Imagine you're a telegraph operator in Boston. It's just before midnight on September 1st, and you're wrapping up your shift. The telegraph system has been acting weird all evening, intermittent issues. Some static on the lines, but nothing too unusual. Then, suddenly, your telegraph key starts clicking on its own. Messages are coming through. Except, nobody's sending them. The needle on your equipment is swinging wildly. Sparks start flying from the telegraph relay. Actual sparks. The paper strip on your recording device catches fire. You disconnect the batteries, the power source for the entire system, figuring that'll stop whatever's happening, except it doesn't. The telegraph keeps working. Without batteries, the lines are somehow generating their own electrical current, enough to send messages across hundreds of miles. You and the operator in Portland, Maine, managed to have a 2-hour conversation using only the mysterious phantom power in the telegraph wires. This wasn't happening in just one place. Telegraph systems across North America and Europe went haywire simultaneously. In Washington, D.C., a telegraph operator received electrical shocks so severe he was thrown backwards from his station. In Norway, telegraph equipment caught fire. In Sweden, the telegraph machines were producing sparks like fireworks. Frederick Royce, a telegraph operator in Boston, reported, "A current of electricity came on the wires so strong that the armature was attracted to and held against the magnet, and the relay magnet became so heated that the covering of the coils of wire upon it was burned off." But wait, it gets weirder. People across the world step outside to see what's causing the chaos and find the sky has lost its mind. Auroras, those shimmering curtains of light usually confined to the Arctic and Antarctic circles, are visible as far south as Cuba, Hawaii and Colombia, in the Caribbean. Ship captains write in their logs about crimson skies so bright they thought nearby ships were on fire. In the Rocky Mountains, gold miners wake up at 1 a.m. thinking it's dawn and start making breakfast. In New York City, people gather in the streets, some thinking the world is ending, others convinced they're witnessing the second coming. One person in Pennsylvania wrote, "The appearance was that of a literal canopy of bright but ever-changing colours. There were the hues of blood on fresh-cut meat the colour of lead, and sometimes of the faint pink of the rose." Another witness in Illinois described great tongues of blood-red flame shooting across the sky. In Australia, literally the other side of the planet, the sky turned deep red, and locals reported being able to read newspaper print by aurora light at midnight. The scientific community was completely baffled. This was 1859. Nobody understood what auroras actually were. The concept of solar wind wouldn't be proposed for another 92 years. The idea that the sun could directly affect Earth's magnetic field, pure speculation. Most scientists still thought auroras were reflections of sunlight off polar ice, or something to do with atmospheric electrical discharge. The notion that a bright flash on the sun could, 17 hours later, cause global electrical mayhem and light up the sky from pole to equator. That would have sounded like magic. But Carrington, brilliant, meticulous Carrington, made the connection. He published a paper suggesting, tentatively, that maybe, possibly, perhaps there was a relationship between what he'd observed on the sun and the geomagnetic storm that followed. The scientific establishment mostly ignored him. The idea seemed too fantastical. How could events on the sun, 93 million miles away, affect Earth? Here's what actually happened. Though we didn't figure this out until the 20th century, Carrington witnessed a coronal mass ejection, or CME. The sun basically belched out billions of tons of plasma superheated, electrically charged particles directly at Earth. This plasma travelled through space at speeds up to 5 million miles per hour, covering the 93 million mile distance in just 17 hours. That's insanely fast for a CME. Most take 2 to 3 days to reach us, when this wall of charged particles slammed into Earth's magnetic field. It compressed and deformed it so severely that the magnetosphere, our planet's invisible shield, essentially collapsed on the day side and stretched way out on the night side, like a windsock in a hurricane. This compression and release created massive electrical currents in Earth's upper atmosphere and, by induction, in anything conductive on the ground. Like, say, thousands of miles of telegraph wires, doctor, Louis J. Lanzarotti from Bell Laboratories later calculated that the induced currents in telegraph wires during the Carrington event were strong enough to power the entire system without batteries. In some cases, the induced voltage exceeded 1000 volts. For context, telegraph systems normally operated on about 80 volts. That's like your phone charger suddenly delivering 15 times more power than it's supposed to. Things are going to catch fire. The Carrington event had an estimated strength of minus 850 nanoteslas on the disturbance storm time index, which is the scale we use to measure geomagnetic storms. To give you perspective, a strong geomagnetic storm today is anything over minus 100 nanoteslas. Carrington was 8.5 times that. The most powerful storm in recent decades, the March 1989 Quebec blackout event, measured minus 589 nanoteslas. That storm knocked out power to 6 million people for 9 hours and caused $2 billion in damage. Carrington was 45% stronger. But here's the truly terrifying part. In 1859, human civilization ran on steam, horsepower, and a relatively primitive telegraph network. That was it. No power grids, no satellites, no internet, no GPS, no cellular networks, no computerized banking, no air traffic control, no hospital life support systems, no water treatment plants with electronic controls, no supply chain management systems, no nothing. The Carrington event happened in a world that was almost entirely analog and mechanical, and it still managed to cause chaos. So what would happen if a Carrington-class event hit us today? In 2008, the National Academy of Sciences commissioned a study to answer exactly that question. The report, titled Severe Space Weather Events: Understanding Societal and Economic Impacts, laid out a scenario that reads like a disaster movie script. A Carrington-level storm hitting modern Earth would cause between $1 trillion and $2 trillion in damage in the first year alone. That's roughly 20 times the cost of Hurricane Katrina, with recovery taking 4 to 10 years. 4 to 10 years. Here's why modern civilization is utterly dependent on long-distance electrical transmission. Power grids use transformers, massive, expensive, custom-built pieces of equipment that step voltage up and down for efficient transmission. These transformers are basically huge coils of wire wrapped around metal cores, perfect for inducing electrical currents during a geomagnetic storm. The Quebec blackout in 1989. That was caused by transformer failure. Just one transformer, a Carrington-level event, would take out hundreds simultaneously across North America, Europe, and Asia. And here's the really fun part: we don't keep spare transformers lying around. Each one is custom-built, weighs up to 400 tons, costs millions of dollars, and takes 12 to 18 months to manufacture and install. We'd be looking at continental-scale blackouts lasting months, possibly years in some regions. No power means no water treatment, no refrigeration, no gas pumps, those run on electricity assisted. Remember, no banking, ATMs don't work, card readers don't work, bank servers don't work. Supply chains collapse because modern logistics are entirely computerized. Hospitals run on backup generators for maybe 72 hours before fuel runs out. Then the life support machines go dark. Oh, and all those satellites we rely on, the ones that handle GPS, weather forecasting, communications, military operations, and about 1,000 other critical functions. Solar radiation from a Carrington-level event would fry their electronics, rendering thousands of satellites into very expensive orbiting paperweights. Have you ever thought about how much of your daily life depends on satellites working your phone's navigation? Your credit card transaction being verified, the weather forecast you checked this morning, the TV show you're streaming, all of it gone. But before we spiral into complete existential dread, there's actually something we need to understand about how these solar storms work, why they're so devastating, and most importantly, why scientists are connecting the dots between Carrington, Tunguska, and our new interstellar visitor in ways that might change everything we thought we knew about cosmic threats. September 1st, 1859, 11:18 a.m., Redhill, England. Richard Carrington is doing what he does every clear morning, observing the sun. Now, before you think, wait, isn't staring at the sun a terrible idea? You're absolutely right. But Carrington isn't some amateur with a death wish. He's a wealthy amateur astronomer with a proper solar telescope, projecting the sun's image onto a white screen in his private observatory. He's been tracking sunspots daily for years, meticulously drawing their positions, trying to understand these mysterious dark patches on our star's surface. On this particular morning, he's sketching a cluster of unusually large sunspots when something happens that shouldn't be possible. Two intensely bright spots suddenly appear in the middle of the sunspot group. Not dark spots, bright ones. Brilliant. White light flares so intense they're visible even against the sun's overwhelming brightness. Carrington literally jumps back from his telescope. In his own words, written later that day, I was suddenly surprised at the appearance of a very brilliant star of light, much brighter than the sun's surface. He rushes to find anyone to witness this with him. He grabs the first person he can find in his house. By the time they return to the observatory, maybe 60 seconds later, the bright spots are already fading. The whole event lasts less than 5 minutes. Carrington makes careful notes, draws detailed sketches, and like any good scientist wonders if anyone else saw it. Turns out, one other person did. Richard Hodgson, another amateur astronomer about 8 miles away, independently witnessed and recorded the exact same phenomenon at the exact same time. 2 witnesses, 1 event, and absolutely no idea what they'd just seen. What Carrington didn't know, what he couldn't possibly know in 1859, was that he'd just witnessed the largest solar flare ever recorded in human history, and the sun wasn't done, not even close. 17 hours later, all hell broke loose. Imagine you're a telegraph operator in Boston. It's just before midnight on September 1st, and you're wrapping up your shift. The telegraph system has been acting weird all evening, intermittent issues, some static on the lines, but nothing too unusual. Then, suddenly, your telegraph key starts clicking on its own. Messages are coming through, except nobody's sending them. The needle on your equipment is swinging wildly. Sparks start flying from the telegraph relay. Actual sparks. The paper strip on your recording device catches fire. You disconnect the batteries, the power source for the entire system, figuring that'll stop whatever's happening. Except it doesn't. The telegraph keeps working. Without batteries, the lines are somehow generating their own electrical current, enough to send messages across hundreds of miles. You and the operator in Portland, Maine, managed to have a 2-hour conversation using only the mysterious phantom power in the telegraph wires. This wasn't happening in just one place. Telegraph systems across North America and Europe went haywire simultaneously. In Washington, D.C., a telegraph operator received electrical shock so severe he was thrown backwards from his station. In Norway, telegraph equipment caught fire. In Sweden, the telegraph machines were producing sparks like fireworks. Frederick Royce, a telegraph operator in Boston, reported, "A current of electricity came on the wires so strong that the armature was attracted to and held against the magnet, and the relay magnet became so heated that the covering of the coils of wire upon it was burned off." But wait, it gets weirder. People across the world step outside to see what's causing the chaos, and find the sky has lost its mind. Auroras, those shimmering curtains of light usually confined to the Arctic and Antarctic circles, are visible as far south as Cuba, Hawaii, and Colombia in the Caribbean. Ship captains write in their logs about crimson skies so bright they thought nearby ships were on fire. In the Rocky Mountains, gold miners wake up at 1 a.m. thinking it's dawn and start making breakfast. In New York City, people gather in the streets, some thinking the world is ending, others convinced they're witnessing the second coming. One person in Pennsylvania wrote, "The appearance was that of a literal canopy of bright but ever-changing colours. There were the hues of blood on fresh-cut meat the colour of lead, and sometimes of the faint pink of the rose." Another witness in Illinois described great tongues of blood-red flame shooting across the sky. In Australia, literally the other side of the planet, the sky turned deep red, and locals reported being able to read newspaper print by aurora light at midnight. The scientific community was completely baffled. This was 1859. Nobody understood what auroras actually were. The concept of solar wind wouldn't be proposed for another 92 years. The idea that the sun could directly affect Earth's magnetic field, pure speculation. Most scientists still thought auroras were reflections of sunlight off polar ice, or something to do with atmospheric electrical discharge. The notion that a bright flash on the sun could, 17 hours later, cause global electrical mayhem and light up the sky from pole to equator, that would have sounded like magic. But Carrington, brilliant, meticulous Carrington, made the connection. He published a paper suggesting, tentatively, that maybe, possibly, perhaps there was a relationship between what he'd observed on the sun and the geomagnetic storm that followed. The scientific establishment mostly ignored him. The idea seemed too fantastical. How could events on the sun, 93 million miles away, affect Earth? Here's what actually happened. Though we didn't figure this out until the 20th century, Carrington witnessed a coronal mass ejection, or CME. The sun basically belched out billions of tons of plasma superheated, electrically charged particles directly at Earth. This plasma travelled through space at speeds up to 5 million miles per hour, covering the 93 million mile distance in just 17 hours. That's insanely fast for a CME. Most take 2 to 3 days to reach us. When this wall of charged particles slammed into Earth's magnetic field, it compressed it so severely that the magnetosphere, our planet's invisible shield, essentially collapsed on the day side and stretched way out on the night side, like a windsock in a hurricane. This created massive electrical currents in Earth's upper atmosphere, and, by induction, in anything conductive on the ground, like, say, thousands of miles of telegraph wires. Dr. Louis J. Lanzarote from Bell Laboratories later calculated that the induced currents in telegraph wires during the Carrington event were strong enough to power the entire system without batteries. In some cases, the induced voltage exceeded 1000 volts. For context, telegraph systems normally operated on about 80 volts. That's like your phone charger suddenly delivering 15 times more power than it's supposed to. Things are going to catch fire. The kicker: the Carrington event wasn't even the sun's final form. Ice core samples from Greenland, analysed in 2012, revealed evidence of an even more powerful solar storm that hit Earth around 774 AD. The radioactive carbon-14 spike in those ice cores suggests that storm was possibly twice as strong as Carrington. Twice. But because it happened in the early medieval period, before telegraph systems, before electrical grids, before anything remotely electronic, it passed almost unnoticed. A few monasteries in Europe recorded unusual auroras. That's about it. Think about that timing. If the 774 AD event happened today, it wouldn't just knock out power grids, it would potentially set civilization back decades. and we know from tree ring data and ice cores that these superstorms happen roughly once every 500 to 1000 years. The last confirmed one was 251 years ago. We're overdue. But here's where things get really interesting and a bit unsettling. Recent research has started questioning whether events like Tunguska and Carrington might be connected in ways we never imagined. Not directly. A solar storm doesn't cause asteroid impacts, but statistically, Dr. Victor Klube from Oxford University spent years analysing historical records and found something peculiar. Major meteor events and intense solar activity seem to cluster in certain periods. His theory, our solar system periodically passes through debris fields left by comets, and these same periods coincide with heightened solar activity cycles, which brings us right back to 3I/Atlas, our interstellar visitor that we barely detected in time, because if there's one thing that connects all three events, the cosmic near miss, the Siberian explosion, and the solar superstorm, it's this uncomfortable truth we're not nearly as safe as we think we are. And the universe doesn't send warning letters. So what exactly happens when Earth's defences get overwhelmed? What's the science behind these catastrophic events? And more importantly, how do we know when the next one is coming? Let's talk about what actually happens when something from space decides to ruin your day, because understanding the science makes it both more fascinating and more terrifying. You need to understand something fundamental. Earth is constantly under bombardment. Right now, as you're listening to this, about 100 tons of space material hits our atmosphere every single day. Most of it is tiny dust particles, small pebbles, the cosmic equivalent of sand. They burn up harmlessly as shooting stars. You've probably wished upon a few dozen vaporized space rocks without even knowing it. But size matters. A lot. Objects smaller than about 80 feet across typically explode in the atmosphere without causing ground damage. These are called airbursts, and they're more common than you'd think. NASA's Center for Near-Earth Object Studies estimates we get a Tunguska-scale airburst roughly once every 100 to 300 years. A Chelyabinsk-scale event, that's the meteor that exploded over Russia in 2013, injuring about 1/500 people, happens every 60 to 100 years. Here's where the math gets uncomfortable. We've been seriously tracking near-Earth objects for only about 30 years. That's not even half of one Tunguska cycle. It's like watching the ocean for 30 minutes and declaring you understand tsunamis. Dr. Alan W. Harris, one of the leading experts in impact hazard assessment, put it bluntly in a 2017 interview. We found maybe 95% of the kilometre-sized objects that could cause global catastrophe. But for the 100-metre class, the Tunguska-sized objects, we've probably found less than 30%. These are the ones that keep me up at night because they're big enough to destroy a city, but small enough to sneak up on us. So let's break down what actually happens during an atmospheric impact. Because Hollywood has lied to you about pretty much everything. When an object enters Earth's atmosphere at cosmic velocities, we're talking 25,000 to 160,000 miles per hour, it's not the heat from friction that destroys it. That's myth number one. The real killer is ram pressure. The object is moving so fast that air molecules literally cannot get out of the way. They pile up in front of the object like snow in front of a snowplow, creating a shock wave of compressed air that heats to tens of thousands of degrees. This compressed air acts like a blowtorch pointed directly at the object. Rock, ice, metal doesn't matter. Everything has a breaking point. And when you're subjecting material to pressures equivalent to being at the bottom of the Mariana Trench, while simultaneously heating it to temperatures hotter than the sun's surface, things fall apart catastrophically. The Tunguska object, likely a stony asteroid about 200 feet across, began breaking apart around 30 miles up. By 15 miles altitude, it was fragmenting rapidly. Between 5 and 10 miles up, the entire mass reached what scientists call the ablation threshold, the point where it's losing mass faster than it's penetrating atmosphere. Then, somewhere between 3 and 6 miles above the Siberian forest, the remaining structure gave up entirely. When that happens, all the kinetic energy, the energy of motion, converts to heat and blast wave instantaneously. And we're not talking about a little bit of energy. A 200-foot asteroid travelling at 33,000 mph carries roughly 15 megatons of kinetic energy. That's 15 million tons of TNT equivalent, or about 1000 Hiroshima bombs released in a fraction of a second. The fireball that resulted from Tunguska reached temperatures of about 16,000 degrees Fahrenheit, hot enough to melt rock, vaporize trees, and ignite clothing from 40 miles away. The thermal radiation travelled at the speed of light, arriving instantly. The shockwave, the actual blast of compressed air, travelled at supersonic speeds, taking about 2 minutes to reach ground zero from the explosion altitude. That's why Semyon Semenov felt the heat before he heard the sound or felt the wind. Light speed beats sound speed every time. Now compare that to a ground impact. When something actually makes it to the surface intact, which only happens with very large or very dense objects, the physics changes dramatically. The impact creates a crater, yes, but it also vaporizes most of the impactor and a significant portion of the ground it hits. That vaporized material becomes superheated ejecta that's thrown back into the atmosphere, some of it reaching escape velocity and leaving Earth entirely. The Barringer crater in Arizona, also called Meteor Crater, was formed about 50,000 years ago by an iron meteorite roughly 160 feet across. Iron is dense, about 8 times denser than rock, which is why it made it to the ground. The impact released about 10 megatons of energy and created a crater 3/4 of a mile wide. But here's the thing, less than 5% of the original meteorite is actually in the crater. The rest, vaporized, gone. Turned into microscopic spherules of iron scattered across hundreds of square miles, the Chicxulub impact that ended the dinosaurs 66 million years ago. That was a 6-mile-wide asteroid travelling at about 45,000 mph. The energy release was equivalent to 100 million megatons, roughly 10 billion Hiroshima bombs. It created a crater 110 miles wide and 12 miles deep. The impact vaporized the asteroid, vaporized trillions of tons of rock, and threw so much material into the atmosphere that it blocked out the sun for years. Global temperatures dropped by 20-30 degrees Fahrenheit. Photosynthesis stopped, the food chain collapsed, 75% of all species went extinct. And here's the really fun part, Chicxulub scale impacts happen roughly once every 100 million years. The last one was 66 million years ago. We're technically only about 2/3 through the average cycle, so we've got some time. Probably. The universe doesn't really care about averages. But let's talk about frequency, because this is where most people's intuition completely fails them. Objects like Tunguska 140 to 260 feet across, 10-15 megaton range hit Earth every 100 to 300 years on average. The last confirmed one was 116 years ago. The Chelyabinsk meteor in 2013 was smaller, about 65 feet across, roughly 500 kilotons. That's in the 60 to 100 year category. And guess what? It had been exactly 105 years since Tunguska. Right on schedule. Objects in the 1 kilometer range, civilization threatening but not species ending, hit roughly every 500,000 years. Objects in the 5 kilometer range, potential extinction events every 20 million years or so. And Chicxulub scale apocalypses every 100 million years, give or take. Here's where it gets psychologically weird, those are averages. averages mean nothing for prediction. You could get 3 Tunguska scale events in a decade. They're nothing for 500 years. It's like Russian roulette. The cylinder doesn't remember previous spins. Every orbit Earth completes around the Sun. We're spinning the chamber again. Dr. Mark Boslow from Los Alamos National Laboratory, who spent his career modelling impact events, explained it to me like this in a 2019 interview. People think of asteroid impacts like they think of earthquakes, something that happens in specific places on a schedule. But it's not like that at all. Every second of every day, Earth occupies a different point in space. We're moving at 67,000 miles per hour around the Sun. That's 18 miles per second. In the time it took you to read this sentence, Earth moved 180 miles through space. We're constantly sweeping through new regions of the solar system, rolling the dice over and over. And those dice are loaded. Our solar system isn't empty. It's full of debris. The asteroid belt between Mars and Jupiter contains millions of objects. The Kuiper belt beyond Neptune, trillions. The Oort cloud, way out at the edge of the solar system, billions of comets, just waiting for something, a passing star. A gravitational perturbation. Pure random chance to kick them into the inner solar system toward us. But here's what really should concern you. Orbital dynamics are chaotic. And I don't mean chaotic like messy. I mean chaotic in the mathematical sense. Tiny changes in initial conditions produce wildly different outcomes. An asteroid that passes harmlessly by Earth this decade might, due to gravitational interactions, be on a collision course next time around. Jupiter, our supposed protector, that's supposed to sweep up dangerous objects, sometimes flings things inward instead of deflecting them outward. The 2013 Chelyabinsk meteor, nobody saw it coming. Not one telescope, not one detection system. A 65-foot rock travelling at 42,000. And we had zero warning. It approached from the direction of the sun,
where telescopes can't look without damaging their sensors.
By the time it entered the atmosphere, we had about 32 seconds before impact. That's not even enough time to send a tweet. The explosion injured about 500 people, mostly from broken glass. The shockwave shattered windows across 6 cities. It was the largest recorded object to hit Earth's atmosphere since Tunguska, and we detected it exactly 0 seconds in advance. The Russian Academy of Sciences estimated the energy release at about 500 kilotons, roughly 30 times the Hiroshima bomb. Yet it was small enough that our detection systems missed it completely. Now scale that up to Tunguska size 4 times larger, releasing 30 times more energy, and imagine it hitting not over Siberian wilderness, but over New York, London, Tokyo, or Los Angeles. The death toll would be in the millions. And we'd have the same amount of warning, none. This is the nightmare scenario that keeps planetary defense scientists awake at night, not the planet killers we can see coming from decades away, but the city killers that show up with hours or minutes of warning if we're lucky. But asteroids and comets aren't the only existential dice rolls we're making. Remember those solar storms, turns out? Those obey similar statistical distributions. The Carrington event wasn't a one-off. It's just the most recent one that hit technological civilization. And the science behind why solar storms devastate our technology is both beautiful and absolutely terrifying in ways that make asteroid impacts look straightforward. In 2015, a team of Russian scientists led by Dr. Andrei Olkovatov published something that made a lot of people in the scientific community very uncomfortable. They'd been analysing historical records, ice core data, and tree ring samples, looking for patterns. What they found was strange. Major meteor events and intense geomagnetic storms seemed to cluster together. Not always, but often enough that it couldn't be pure coincidence. The Tunguska event in 1908 that year also saw unusual aurora activity across Europe. the Chelyabinsk meteor in 2013. It happened during a period of elevated solar activity. Go back further, the Great Meteor Procession of 1783, where thousands of people across Europe watched a spectacular fireball train cross the sky. That same year saw one of the most intense aurora displays of the 18th century, visible as far south as Rome. Now, before you start thinking conspiracy theory, let me be clear, nobody's suggesting solar storms cause asteroid impacts or vice versa. That's not how physics works. But what if both phenomena are symptoms of something larger happening in our solar system? Dr. Victor Klube from Oxford University. Yeah, we mentioned him earlier, spent decades developing what he calls the coherent catastrophism theory. His idea, controversial but increasingly supported by data, is this: our solar system periodically passes through dense regions of cosmic debris, remnants of ancient comets that broke apart millions of years ago. When we transit these regions, two things happen simultaneously. First, we encounter more impact threats, more meteors, more bolides, more potential Tunguska-scale airbursts. That part's straightforward. But second, and this is where it gets weird, the increased cosmic ray flux from all this debris might affect the sun's magnetic field behavior, potentially triggering more CME activity. Sound crazy, maybe, but cosmic rays do affect Earth's climate and atmosphere in measurable ways. The Svensmark effect, named after Danish physicist Henrik Svensmark, demonstrates that cosmic rays influence cloud formation. More cosmic rays mean more clouds, which affects global temperature. If cosmic rays can affect Earth's atmosphere from 93 million miles away, is it really that absurd to suggest they might affect the sun's behavior, Doctor? Richard Muller from UC Berkeley analysed ice core data going back 400,000 years and found something peculiar. Ice ages and interglacial periods correlate with Earth's passage through the galactic plane, the flat disk of the Milky Way where matter is denser. Every 30 million years or so, our solar system bobs up and down through this plane like a cork in water. When we pass through the dense regions, impact rates go up. Extinction events become more common. Climate destabilizes. We're not saying the Tunguska event and solar storms are directly connected. But what if they're both part of a larger pattern we're only now beginning to recognize? What if our solar system moves through cosmic neighborhoods that are sometimes safe and sometimes not? Here's where 3/Atlas becomes really interesting. Remember, it's an interstellar object it came from outside our solar system. Its trajectory, when traced backwards, suggests it originated somewhere in the direction of the Pleiades star cluster, roughly 440 light-years away. That's a long journey. Along the way, it's been exposed to the interstellar medium cosmic rays, magnetic fields, maybe even the shock waves from distant supernovae. Doctor. Abraham Loeb, yes. Him again published a paper in 2020 suggesting that interstellar objects might actually carry information about the cosmic environment they pass through, like message bottles floating in the ocean, except the ocean is space, and the message is written in isotope ratios and impact scars. 3/Atlas. Passed through how many stellar neighborhoods on its way here? What did it encounter? What does its composition tell us about the conditions out there in the galaxy? But here's the thought that should really make you uncomfortable if 3/Atlas came from interstellar space. It's following a trajectory shaped by forces outside our solar system. Its path was determined by gravitational interactions with stars we can barely see, perturbations from objects we haven't discovered, maybe even influences from dark matter structures we don't understand. And it came within spitting distance, astronomically speaking, of hitting us. What are the odds of that, Doctor? Amaya Morrow-Martin from the Space Telescope Science Institute did the calculation. Given the estimated population of interstellar objects and Earth's cross-sectional area as a target, the probability of an interstellar impact in any given century is roughly 1 in 100 million. Those seem like good odds. Right. Except we've detected 3 interstellar objects in 7 years. 3. Either we're spectacularly unlucky, or more likely there are way more interstellar objects passing through than we thought. Dr. Morrow-Martin's colleague, Dr. Gregory Laughlin from Yale, recalculated based on the new detection rate. His estimate: we might be seeing interstellar objects because our detection technology finally got good enough, and the actual population could be 10 to 100 times higher than previous models suggested. That changes the math dramatically. If there are 10 times more interstellar objects than we thought, that 1 in 100 million becomes 1 in 10 million. Still unlikely in any given year, but over millennia, over the span of human civilization, the probability starts looking uncomfortable. And unlike solar storms, which we can predict somewhat based on solar cycles, interstellar objects are completely random. They come from directions we're not watching, at speeds we don't anticipate, with compositions we can't predict until we measure them. 3I/Atlas was icy a comet. The next one might be solid iron, or it might be a loosely bound rubble pile that fragments in the atmosphere, creating multiple Tunguska-style airbursts simultaneously across a continent. NASA's Planetary Defense Coordination Office. Yes, that's still their real name, maintains a catalogue of near-Earth objects. As of 2024, they've identified about 32,000 asteroids, larger than 140 meters. That sounds like a lot until you realize they estimate there are about 25,000 more they haven't found yet. And those are just the objects in our solar system. Following predictable orbits, we can calculate decades in advance. Interstellar objects. We have maybe 18 hours of warning if we're lucky. More likely, we spot them on their way out after they've already passed through the inner solar system. Oumuamua, the first confirmed interstellar object, we discovered it 2 weeks after its closest approach to Earth. It was already leaving when we noticed it. If it had been on a collision course, we would have had 0 warning, 0 time to prepare, 0 options except to watch it happen. Dr. Linley Johnson, NASA's Planetary Defense Officer, and yes, that's also his actual title, gave a presentation to Congress in 2019 that I'll never forget. A representative asked him, what would you do if you detected an asteroid on an impact trajectory with 24 hours of warning? Johnson's response was brutally honest. Pray. That's it. That's the plan. Because deflecting an asteroid requires months of preparation and years of advance notice. You can't just nuke an asteroid that's Hollywood nonsense. Nuclear weapons in space are prohibited by treaty anyway, but even if they weren't, blowing up an asteroid just turns one bullet into a shotgun blast. Now instead of one impact, you've got dozens or hundreds of smaller impacts scattered across a wider area. Congratulations, you've made it worse. The actual deflection techniques we're developing, kinetic impactors like NASA's DART mission, gravity tractors, even exotic proposals involving solar sails or ion beam shepherds all require time. Years of time. You need to change the asteroid's velocity by a tiny amount, maybe a few millimeters per second. Years before impact, so that tiny change adds up to missing Earth by thousands of miles. With 24 hours of warning, you can't change the asteroid's trajectory. You can maybe evacuate the impact zone if you know exactly where it's going to hit, which requires tracking data we might not have for a newly discovered object. More likely, you just warn people to stay away from windows and take shelter in basements. That's about the extent of 24-hour planetary defense. But at least with asteroids, we're building better detection systems. The Vera C. Rubin Observatory will survey the sky every few nights once it's operational. NASA's NEO Surveyor Space Telescope, launching in 2027, will spot asteroids we can't see from ground-based telescopes. The European Space Agency's Fly telescope network will automate detection. We're getting better. Solar storms. Though our warning system for those is exactly one satellite, NOAA's Deep Space Climate Observatory, sitting at the L1 Lagrange point between Earth and the Sun, about 1 million miles away. One satellite. If it fails, and satellites do fail, we're blind. The backup is ground-based coronagraphs and solar observatories, which give us maybe a few hours less warning. And here's the really fun part, both threats are getting worse. Not because space is getting more dangerous, but because we're getting more vulnerable. Every year, we launch more satellites, we build more interconnected power grids, we make our supply chains more efficient, which means more just-in-time delivery and less redundancy. We digitize more critical infrastructure. We make everything depend on everything else. It's incredibly efficient when it works, when it breaks cascading failures across every system simultaneously. A Carrington event in 1859 burned some telegraph wires and created pretty lights. The same event today could set civilization back decades. A Tunguska event in 1908 flattened empty forest. The same event over modern New York or Tokyo, 8 million people in the immediate blast zone, with millions more affected by infrastructure collapse, fires, and the breakdown of emergency services. We've built a world that's exquisitely sensitive to disruptions we can't prevent and can barely predict. And the universe, which has been mostly polite about not hitting us lately, doesn't owe us continued good luck. So maybe, just maybe, these three events we've been discussing aren't just interesting historical coincidences. Maybe they're warnings, evidence that the universe occasionally reaches out and taps us on the shoulder, reminding us we're not as secure as we pretend to be. The question is, are we paying attention because the next tap might not be gentle? Let me paint you a picture of what 2012 should have been what it almost was. July 23rd, 2012. It's a Monday morning, you wake up, check your phone, except your phone doesn't work. The screen's dead. You try turning it on. Nothing. Weird. You figure the battery died overnight, so you plug it in to charge. The charger doesn't work either. Actually, now that you're paying attention, nothing in your house works. No lights, no refrigerator hum, no air conditioning. The digital clock on your microwave is blank. You look outside. Your neighbour's standing in his driveway, looking confused. Someone else is trying to start their car, modern cars with electronic fuel injection and computer-controlled systems. It's not starting. Down the street you see smoke rising, a lot of smoke. Later, you'll find out it's a transformer fire. One of hundreds happening simultaneously across the continent. You try your phone again, thinking maybe it's just your house. Still nothing. You don't know it yet, but every cell tower within 500 miles is offline. The satellites they depend on, about 40 of them are dead or dying. Their electronics fried by radiation levels they were never designed to handle. Your phone's not broken, there's just nothing for it to connect to anymore. By noon, you realise the power's not coming back on anytime soon. By evening, you notice the stores are chaos, people panic buying anything they can get with cash. Because credit cards don't work without electricity, and ATMs are just expensive decorative boxes now. By the next morning, you haven't had water since yesterday because the municipal pumps need electricity. The sewage system's backing up. Your neighbour, who depends on an electric medical device, is in serious trouble. This isn't science fiction. This is what Dr. Daniel Baker from the University of Colorado says would have happened if the July 2012 coronal mass ejection had launched 9 days earlier. 9 days. That's the only reason you're not living through this scenario right now. The 2012 CME was fast, one of the fastest ever recorded. It crossed the 93 million miles from Sun to Earth's orbital path in just 17 hours. Stereo A, one of NASA's solar observation satellites, caught the full brunt of it. The radiation levels it measured were comparable to the Carrington event, possibly stronger. Dr. Janet Luhmann from UC Berkeley, who analysed the data, told NASA if it had hit Earth, it probably would have been like the Carrington event of 1859, except way worse, because 1859 didn't have power grids or satellites or any of the technological infrastructure we depend on to survive. Here's what most people don't realise about modern vulnerability. We've optimised everything for efficiency, which is just another way of saying we've eliminated redundancy. The modern electrical grid operates on a principle called N1 reliability. The system can lose any single component and still function. That's great for normal operations. For a Carrington-level storm taking out 300 components simultaneously, that principle becomes N300 catastrophe. The power grid is particularly vulnerable because of something called geomagnetically induced currents, or GICs. When a massive geomagnetic storm hits, it doesn't just affect space and the upper atmosphere, it creates electrical currents in the ground itself. Earth becomes a giant battery, and all those power lines and pipelines become wires connecting the terminals. Doctor. John Kappenman, remember him from earlier, spent years modelling what GICs do to transformers. His simulations showed that a Carrington-level event would create ground currents strong enough to drive transformers into deep saturation within minutes. The transformer cores would heat up rapidly. We're talking internal temperatures exceeding 1000 degrees Fahrenheit. The insulation would fail. Internal arcing would begin. And once a large power transformer fails catastrophically, it's not something you just replace. These aren't your little cylindrical transformers on telephone poles. We're talking about extra high voltage transformers, massive units that can weigh 400 tons, cost $10 million each, and take 12 to 24 months to manufacture. They're custom built for specific locations in the grid. We don't keep warehouses full of spares because they're too expensive and too specialised. The global production capacity is maybe 100 per year, total, for the entire world. A Carrington-level event could destroy 300 to 400 of them across North America alone. Do that math. At 100 per year production capacity, we're looking at 3 to 4 years just to manufacture replacements, assuming the factories that make them still have power, which they won't, because they're also connected to the grid that just failed. But it's not just the power grid. Let's talk about satellites, because this is where the 2012 near miss gets really scary. When that July 2012 CME passed through Earth's orbital space, Stereo A measured particle radiation levels that would have been lethal to satellite electronics. The satellite itself survived only because it's specifically hardened against solar radiation. It's designed to study the sun. After all, commercial satellites. Not so much. Modern satellites are built for efficiency and cost effectiveness, not radiation resistance. Radiation hardening adds weight, expense, and complexity. Most commercial satellites have minimal shielding because, statistically, they're unlikely to encounter extreme radiation during their operational lifetime. It's a calculated risk that works great 99% of the time. A Carrington-level storm is the other 1%. Dr. Mike Hapgood from the Rutherford Appleton Laboratory in the UK studied what happened to satellites during the 2003 Halloween storm, a storm much weaker than Carrington. 59 satellites reported anomalies. 2 failed completely. One was Japan's Adios 2 environmental satellite, $640 million. Gone. The other was Britain's Ministry of Defence satellite Skynet 4F classified loss, but definitely not cheap. Scale that up to Carrington intensity, which is maybe 5 to 10 times stronger. Doctor. Hapgood's estimate 5% to 10% of all satellites in orbit would be damaged or destroyed. That's 250 to 500 satellites out of approximately 5,000 currently active. GPS satellites, communication satellites, weather satellites, military reconnaissance satellites gone or severely degraded. And here's the cascading failure. GPS doesn't just tell you where you are when you're driving. GPS timing signals synchronize everything. Cell phone towers use GPS to coordinate with each other. Power grids use GPS timestamps to balance load across regions. Financial markets use GPS timestamping for high-frequency trading. The internet backbone depends on GPS-synchronized routers. Kill GPS, and you've killed coordination across every major technological system. The financial sector would be hit particularly hard. Dr. Edward Orton from Cambridge University published a study in 2017 estimating that a 12-hour GPS outage would cost the US economy about $1 billion per day. A Carrington event wouldn't give us a 12-hour outage, it would likely destroy multiple GPS satellites permanently, requiring years to rebuild the constellation. But let's talk about something even more immediate aviation. Modern aircraft are flying computers. Every system navigation, communication, fuel management, flight controls depends on electronics. During a severe geomagnetic storm, high-frequency radio communication becomes unreliable or impossible. VHF communication degrades, GPS signals become erratic, radiation levels at cruising altitude spike dramatically during the October 2003 solar storms. Radiation exposure at 35,000 feet was equivalent to getting several chest X-rays per hour. The FAA has protocols for solar storms. When warnings go out, they reroute flights away from polar regions where radiation exposure is highest. They reduce flight altitudes. In extreme cases, they ground flights entirely. But those protocols assume we have warning. They assume communication systems work. They assume air traffic control radar and computer systems are functioning. A surprise Carrington event like the one we almost got in July 2012 would have caught thousands of flights in the air with degraded or failed navigation systems, unreliable communication, and air traffic control systems struggling to track them. The FAA estimated in a 2010 report that a severe geomagnetic storm could force the grounding of all commercial aviation for days to weeks. Every plane, worldwide, simultaneously. What does that do to the global economy? About 10 million people fly every single day worldwide. Supply chains depend on air cargo medicine. Critical components, perishable goods, ground all flights for even a week, and you're looking at hundreds of billions in losses and shortages of critical supplies. And we haven't even talked about things you don't see, the undersea fibre optic cables carrying internet traffic between continents, which have repeaters and amplifiers every 30 to 60 miles. Those amplifiers are electronic. They are also underwater and extremely difficult to access for repairs. A major geomagnetic storm could damage dozens or hundreds of them simultaneously. Suddenly, international internet traffic drops by 30%, 50%, maybe more. Video calls don't work. Cloud services time out. International financial transactions slow to a crawl. The 2008 National Academy of Sciences report the one that estimated $2 trillion in first-year damages called a severe geomagnetic storm, a low-frequency, high-consequence event in the driest possible bureaucratic language. What they meant was it doesn't happen often, but when it does, it ends civilization as we know it. And the really terrifying part, we came within 9 days of finding out if their estimates were accurate. But here's what keeps me up at night even more than that we knew the 2012 CME happened. We saw it. We measured it. We watched it blast through the Earth's orbital space just days after we passed through that region. NASA published papers about it. Scientists gave talks about how lucky we got. And nothing changed. We didn't build more resilient power grids. We didn't radiation harden our satellite constellations. We didn't create strategic reserves or replacement transformers. We didn't even really tell the public how close we came to a technological apocalypse. Because explaining that we dodged civilizational collapse by pure timing luck tends to make people uncomfortable. Dr. Ashley Dale from Bristol University put it bluntly in a 2020 interview. We're playing Russian roulette with the sun every solar cycle. We're pulling the trigger. Eventually, the chamber won't be empty. And the sun doesn't care about our emergency plans, or our insurance policies, or our disaster preparedness drills. The sun is a giant fusion reactor wrapped in chaotic magnetic fields. And sometimes not often, but sometimes it points a loaded gun directly at us and fires. July 2012 taught us we can dodge the bullet. But it also taught us something more disturbing even when we see the gun, even when we watch the trigger pull, even when we calculate exactly how close the bullet came to hitting us. We still don't really change our behaviour. We just hope we get lucky again next time. But while we're worrying about the sun and watching for asteroids, there's something else happening that almost nobody's talking about. Something that's been happening for decades, possibly centuries, and we're only now starting to notice the pattern. Because it turns out the universe has been sending us warning shots this whole time. We just weren't paying attention to where they were coming from. Let's talk about the warnings we missed and the ones we're still missing. February 15th, 2013, Chelyabinsk, Russia. It's 9:20 in the morning, and Marat Ahmet-Valeyev is driving to work with his dashboard camera running. If you're not familiar with Russian driving culture, just know that dashboard cams are basically mandatory. Insurance fraud is so common that everyone records everything. Marat's camera is pointed at the road ahead, capturing the usual winter morning traffic. Then the sky catches fire. A brilliant streak of light appears, growing brighter and brighter, until it's painful to look at even through the camera. The fireball is so intense it casts shadows in broad daylight. For a few seconds, the world is bathed in light brighter than the sun. Then it explodes. The shockwave hits about 90 seconds later. Windows shatter across 6 cities. A zinc factory roof collapses. Over 500 people are injured, mostly from flying glass. The blast is so powerful it circles the globe, detected by monitoring stations as far away as Antarctica. The energy release, about 500 kilotons, roughly 30 times the Hiroshima bomb. And nobody saw it coming. Not one telescope, not one detection system, zero warning. Actually, that's not quite true. We had negative warning, if such a thing exists. Because on that exact same day, the exact same day asteroid 2012 DA14 was making its closest approach to Earth, NASA had known about DA14 for months. They'd calculated its orbit precisely. Press conferences were held. News articles were written about this near-miss asteroid that would pass within 17,200 miles of Earth, closer than our geostationary satellites. Everyone was watching DA14. Every telescope, every camera, every news crew. And while we were all looking in that direction, the Chelyabinsk meteor came from a completely different part of the sky and smacked us without warning. The irony was so perfect it felt like the universe was mocking us. Doctor. Paul Chodas from NASA's Center for Near-Earth Object Studies later told reporters, the Chelyabinsk event is what we call a cosmic coincidence. 2 unrelated near-Earth objects arriving on the same day. The odds of that happening by chance are roughly 1 in 100, 0, 0, 0. 1 in 100, 0, 0, 0, and yet it happened. Or maybe, and this is where things get uncomfortable, maybe it wasn't coincidence at all. Stay with me here. I'm not suggesting some grand conspiracy or intelligent design. But what if both objects were part of the same general debris stream that Earth happened to be passing through? What if February 15th, 2013 wasn't special because 2 random objects showed up, but because Earth's orbit carried us through a region of space that had higher than average debris density. Dr. Peter Brown from Western University in Ontario spent years analysing meteor detection data from infrasound stations. These are sensors that detect low-frequency sound waves from explosions and atmospheric events. What he found was disturbing small Chelyabinsk-scale airbursts happen way more often than we thought. His 2013 paper documented 26 airbursts between 1 and 600 kilotons that occurred between 2000 and 2013. That's roughly 2 per year. 2 per year of explosions powerful enough to level buildings, and we only noticed the ones that happened over populated areas or were caught on camera. How many happened over oceans, over a remote wilderness, over the poles? We don't know. We literally don't know how many times Earth gets hit by city-killer-scale objects because 70% of Earth's surface is ocean, and another significant chunk is uninhabited wilderness. If Chelyabinsk had exploded over the Pacific instead of Siberia, we might never have known it happened. But it's not just small stuff. In 1972, August 10th, to be exact, a meteor estimated at 3 to 14 meters across entered Earth's atmosphere over Utah, skipped like a stone across the upper atmosphere, and left without hitting us. It was captured on film. Thousands of people saw it. The object was essentially doing what Apollo capsules do during re-entry, using the atmosphere to slow down and change trajectory. Except this was a rock doing it naturally. It came within 57 kilometers of Earth's surface. That's 35 miles. For context, the boundary of space, the Kármán line, is 62 miles up. This thing came within 35 miles of the surface and then left. If it had entered at a slightly steeper angle, it would have hit probably somewhere in the northern United States or southern Canada. Instead, it bounced off our atmosphere and returned to space. We got lucky, again. The 1972 event and the 2013 Chelyabinsk meteor share something interesting. Both came from the direction of the sun. Not literally from the sun, but from that general direction in the sky. This matters because telescopes can't look toward the sun without damaging their sensors. It's a massive blind spot in our detection network. An object approaching from the sun's direction is essentially invisible until it's already here. Dr. Christina Thomas from Northern Arizona University, who worked on NASA's DART mission, explained it to me like this. Imagine you're driving, and someone tells you to watch for oncoming traffic, but also you can't look out the windshield because the sun's too bright. That's basically where we are with asteroid detection. We can see objects approaching from most directions, except the most dangerous one, the direction they're most likely to come from if they're in sun-grazing orbits. And here's the thing, a lot of objects are in sun-grazing orbits. Comets especially. The sun's gravity pulls things toward it. Objects that survive close passes get flung outward, but they come back. And when they do, they're coming from the sun's direction. This isn't theoretical. In October 2017, Oumuamua, the first confirmed interstellar object, approached from the direction of the constellation Lyra. But by the time we detected it, it was already past the sun and leaving. We spotted it by chance because an automated survey happened to be looking at the right patch of sky at the right time. If it had been aimed at Earth instead of just passing through the solar system, we would have had no warning whatsoever. Then in 2019, Tui/Borisov, the second interstellar object, was discovered by amateur astronomer Gennady Borisov using a homemade telescope, not Hubble, not the Very Large Telescope, not any of NASA's fancy detection systems. A guy in Crimea with a telescope he built himself in his backyard. He found an interstellar comet before the world's most advanced detection networks did. That should terrify you. It terrifies me. And now 3. I/Atlas in 2024 detected after it had already passed Mars's orbit. 3 interstellar objects in 7 years, all discovered basically by luck. all detected far too late to do anything if they'd been on collision courses. But let's zoom out for a second, because there's a bigger pattern here that nobody wants to talk about. Doctor William Napier from Cardiff University has been studying meteor streams and historical records for decades. His research suggests that Earth's orbit periodically takes us through dense regions of cosmic debris remnants of ancient comets that broke apart thousands or millions of years ago. These debris streams aren't uniform, they're clumpy. Most of the time, we pass through empty space. But occasionally, we hit a dense pocket. When that happens, meteor activity increases across the board. More fireballs, more impacts, more air bursts. And here's the disturbing part. These periods of heightened impact risk seem to correlate with other historical disasters. Not cause them directly, but correlate with them. The Late Bronze Age collapse around 1200 BCE, when multiple civilizations across the Mediterranean and Near East collapsed, simultaneously coincides with evidence of increased meteor activity. Tree ring data shows climate anomalies. Historical texts mention fires from heaven, and the sky was consumed by flames. The Tunguska event in 1908 happened during a period when meteor observations across Europe and Asia were higher than average. The Chelyabinsk meteor in 2013, that was during a solar maximum, when the sun was more active than usual. Now, correlation isn't causation. Just because two things happen at the same time doesn't mean one caused the other. But what if they're both effects of a common cause? What if heightened solar activity and increased meteor impacts both indicate that our solar system is passing through a more dangerous region of space, Doctor? Napier published a paper in 2015 titled Paleolithic Extinctions and the Taurid Complex that makes an unsettling argument. The Taurid meteor stream, which Earth passes through every year in late October and early November, contains debris from Comet Encke, which broke apart somewhere between 20,000 and 30,000 years ago. But it's not just small pebbles. The Taurid stream likely contains dozens or hundreds of objects in the 100 metre to 1 kilometre range. City killers to civilization enders. We know some of them by name. Asteroid 2015, TX-24, discovered in October 2015, is about 200 metres across, twice the size of the Tunguska object. It's in the Taurid stream. Asteroid 2005 UR, about 400 metres across, is also in the Taurid stream. There are probably more we haven't found yet because they're dark, smallish, and their orbits don't bring them near Earth very often, except when they do. Every few thousand years, Earth's orbital position lines up with the densest part of the Taurid stream. When that happens, impact rates could increase by a factor of 10 or more. And we might be entering one of those periods right now. Not this year, probably not next year, but within the next few decades, Earth will be passing through the densest regions of the Taurid stream that we've encountered in millennia. Dr. Mark Bailey from Armagh Observatory in Northern Ireland, who's studied the Taurid stream for 30 years, told the Royal Astronomical Society in 2019, "We're overdue for a significant impact from the Taurid complex, not a planet killer, but certainly something in the Tunguska range or larger. The statistical likelihood increases every year." And here's the connection nobody wants to make explicitly when Earth passes through dense debris fields. We're also likely encountering increased cosmic ray flux, more interplanetary dust, and potentially more perturbations to the solar system's magnetic environment. All of which could affect solar activity. This is where mainstream science gets uncomfortable, because it sounds too close to astrology or ancient astronaut theories. But the physics is sound. Cosmic rays do affect Earth's climate. Meteor impacts do deposit energy into the atmosphere. Interplanetary dust does affect the solar system's magnetic field. The question isn't whether these effects exist, it's whether they are large enough to matter. And increasingly, the answer seems to be yes, They matter. In 2012 that year, again, a team from Lund University in Sweden published a study showing that Earth's passage through dense interstellar clouds could trigger ice ages by affecting the Sun's heliosphere and allowing more cosmic rays to reach Earth's atmosphere. The effect is real, measurable, and significant over geological timescales. So here's the uncomfortable possibility. The events we've been discussing 3/Atlas's close pass. The Tunguska explosion. The Carrington event might not be isolated incidents. They might be symptoms of larger patterns we're only beginning to recognize. The universe isn't trying to kill us specifically. It's just that sometimes our solar system's neighbourhood gets rough. And when that happens, multiple bad things can happen at once or in quick succession. The 2012 near miss with the solar superstorm, the 2013 double whammy of Chelyabinsk and DA-14 on the same day, the 2024 detection of 3/Atlas with minimal warning. These aren't coincidences, they're data points. And the more data we collect, the more it looks like we've been living through a period of heightened cosmic risk without realising it. Have you noticed how many meteor fireballs have made the news in the last decade? How many close approach asteroids NASA announces? It's not because space is getting more dangerous. It's because we're finally paying attention and we're finally good enough at detecting these things to see what's always been there. And what's always been there is we're surrounded by objects that can kill us, orbiting a star that can kill us, passing through debris fields that increase the risk, with detection systems that miss most threats until they're already past us. But awareness is the first step. Right, we can't prepare for threats we don't know about. So what are we actually doing about all this? What's the plan when the next Tunguska-scale object appears with 18 hours of warning? Or the next Carrington-class storm launches directly at us? Turns out, we've got some ideas, some good ones, even whether they'll work when we really need them. Well, that's the trillion-dollar question. So what's the actual plan? What happens when NASA calls you up and says, "Hey, we've got an asteroid the size of a football field heading for downtown Chicago in 6 months. What should we do?" First, the good news, we're not completely helpless anymore. For the first time in human history, we have actual, tested technology for deflecting asteroids. Not theoretical, not science fiction, tested. September 26th, 2022, NASA's DART spacecraft double asteroid redirection test. Because apparently someone at NASA still has a sense of humour about the apocalypse slammed into an asteroid called Dimorphos at 14,000 miles per hour. The impact was deliberate, carefully planned, and humanity held its collective breath to see if it would work. It did, spectacularly. Dimorphos is a small asteroid, about 530 feet across, orbiting a larger asteroid called Didymos. Before impact, Dimorphos took 11 hours and 55 minutes to complete one orbit. After DART hit it, the orbital period decreased by 33 minutes. 33 minutes might not sound like much, but Dr. Nancy Chabot from Johns Hopkins Applied Physics Laboratory. The mission lead was ecstatic. We moved an asteroid. We changed its motion in space. This is the first time in history humanity has deliberately altered the motion of a celestial body. The kinetic impactor technique works. We proved it. You slam a spacecraft into an asteroid hard enough and fast enough, and you change its velocity. Not by much. DART changed Dimorphos' speed by about 2.7 millimeters per second. But that tiny change, applied years before a potential impact, adds up to missing Earth by thousands of miles. The key phrase there is years before. Kinetic impactors require warning time. Lots of warning time. The earlier you can nudge an asteroid, the less force you need to make it miss Earth. Hit it 10 years before impact, and a small push works. Wait until 6 months before, and you'd need to hit it with something massive or hit it multiple times to change its trajectory enough. This is why detection is everything. Dr. Linley Johnson, NASA's Planetary Defense Officer, explained it in terms anyone can understand. Asteroid deflection is like trying to change lanes on the highway. If you see the obstacle a mile ahead, a gentle turn of the wheel is enough. If you see it 50 feet ahead, you're going to crash no matter what you do. So we need to see them coming, which brings us to the Vera C, Rubin Observatory, currently under construction in Chile. This thing is a game changer. It has an 8.4 meter primary mirror and a camera with 3.2 billion pixels, the largest digital camera ever built for astronomy. Once operational in 2025, it'll photograph the entire visible sky every 3 nights. Every 3 nights. Anything that moves asteroids, comets, space debris will be tracked automatically. Dr. Mario Jurek, who's working on the Rubin Observatory's data systems, told me the numbers are staggering. We expect to discover about 5 million new asteroids in the first year alone. That's more than all the asteroids discovered in human history in just 12 months. By year 10, we'll have catalogued essentially every asteroid larger than 140 meters in the inner solar system. That's the good news. The bad news. Even with perfect detection, there are scenarios where we're just screwed. Scenario 1, the interstellar interloper. Remember, 3 ice/8-less objects coming from outside the solar system can be travelling way faster than local asteroids, up to 100 kilometers per second or more. At those speeds, even if we detect them months in advance, we don't have anything that can catch up to them. Our fastest spacecraft, New Horizons, travels at about 16 kilometers per second. An interstellar object moving at 100 kilometers per s is outrunning anything we could launch by a factor of 6. If an interstellar asteroid was on a collision course with Earth, and we detected it with 6 months' warning, our options would be evacuate the impact zone and pray it doesn't hit somewhere too catastrophic. That's it. That's the plan. Scenario 2, the long-period comet. These are comets with orbital periods of hundreds or thousands of years. They spend most of their time way out past Neptune, then occasionally plunge into the inner solar system at ridiculous speeds. The problem, we can't detect them until they get close. And by the time they're close, they're moving too fast and have too much mass for kinetic impactors to work. Dr. Joseph Newth from NASA's Goddard Space Flight Center testified before Congress in 2016 about this exact threat. If we detected a 1-kilometer comet on a collision course with Earth, with typical warning time of maybe 1 to 3 years, we currently have no way to stop it. None. The comet would be moving too fast, would be too massive, and we wouldn't have enough time to develop and launch an adequate deflection mission. His recommendation: build deflection spacecraft now, in advance, and keep them ready to launch on short notice. It's like having fire extinguishers in your building before the fire starts. Congress listened politely, nodded, and didn't fund it. Because spending billions on spacecraft to defend against a threat that statistically might not arrive for centuries isn't politically popular. Scenario 3, the rubble pile. Not all asteroids are solid rocks. Many, maybe most, are what scientists call rubble piles. They're collections of smaller rocks held together by weak gravity, like a loose gravel pile in space. Hit one with a kinetic impactor, and instead of deflecting the whole thing, you might just blast it apart into dozens of smaller pieces, all still heading for Earth. Now, instead of one impact, you've got a shotgun blast scattered across hundreds of miles. The solution: don't hit it in the centre. Hit it off to the side, at an angle, to give it a spin or a nudge without fragmenting it. But that requires knowing the asteroid's composition, structure, and rotation beforehand, which requires sending a reconnaissance mission first, which requires time we might not have. Then there's the nuclear option, and I mean that literally. Despite what Hollywood tells you, we're not going to nuke asteroids by landing on them and drilling holes to place charges. That's ridiculous. But nuclear devices detonated near not on an asteroid could vaporize surface material. The expanding gas from that vaporization would act like a thruster, pushing the asteroid off course. This is called a nuclear standoff burst, and it's actually the most powerful deflection method we have. A single well-placed nuclear explosion could deflect an asteroid that would require dozens of kinetic impact emissions. The physics works. Computer simulations confirm it. The problem, we've never tested it. The Outer Space Treaty of 1967 bans nuclear weapons in space. Testing a nuclear standoff burst would require international cooperation and treaty modifications, which takes years of diplomatic negotiation. Dr. Bong Wee from Iowa State University has been advocating for this technology for decades. His team designed a concept called HAIV Hypervelocity Asteroid Intercept Vehicle that would first hit the asteroid with a kinetic impactor to create a crater, then detonate a nuclear device inside that crater for maximum effect. It's elegant. It would work. And it's completely unfunded because nobody wants to be the politician who advocates for nuclear weapons in space, even if the purpose is planetary defense. But here's the real problem with all these asteroid deflection techniques. They assume we have time and accurate information. Most scenarios go like this. We detect asteroid X. We have 5 years to impact. We launch a mission. It arrives in 2 years. We study the target. We launch a deflection mission. Success. Very neat, very clean, very optimistic. Reality is messier. The Chelyabinsk meteor gave us 0 warning. 3I/Atlas was detected after it was already inside Mars's orbit. The hypothetical interstellar object heading our way might be spotted with 3 months of warning, not enough time to build a spacecraft, let alone launch it to intercept. And that's just asteroids. Solar storms are a different nightmare entirely. For solar storms, as deflection options are, well, we don't have deflection options. You can't deflect 1 billion tons of plasma travelling at 5 million miles per hour. It's coming, and you just have to deal with it. So the strategy shifts from deflection to mitigation, reducing damage, rather than preventing the event entirely. The power grid is the critical vulnerability. Dr. John Kapperman's firm, Storm Analysis Consultants, has proposed a solution: install neutral current blockers at key transformer locations. These devices prevent geomagnetically induced currents from entering transformers. They're not even that expensive, maybe $50 000 to $100 000 per unit. For a few $billion, you could protect the entire North American grid. Guess how many have been installed? Take a guess. As of 2024, fewer than a dozen critical transformers have neutral current blockers installed, out of thousands. The problem isn't technology, it's bureaucracy and cost allocation. Who pays for it? The federal government, state, utilities, private power companies. Everyone agrees it's important, but nobody wants to pay for protection against something that hasn't happened yet. It's the same problem we have with earthquake retrofit in buildings in California, or flood defences in coastal cities. Everyone knows the disaster is coming eventually, but eventually could be next year or next century, and infrastructure spending for disasters that haven't happened yet is politically difficult. Meanwhile, other countries are taking it more seriously. The UK government commissioned a study in 2015 that concluded a Carrington-level event would cause £15 billion in damage to British infrastructure. In response, they've started hardening critical systems and developing emergency protocols. The European Space Agency is building a space weather forecasting system. Japan has implemented grid protection measures after seeing what happened to Quebec in 1989. The United States, We have NOAA's Space Weather Prediction Center, which does excellent work monitoring the sun and issuing forecasts. But in terms of actual grid hardening, actual infrastructure protection, actual preparation for a Carrington-level event, we're nowhere near ready. Dr. Daniel Baker from the University of Colorado, who's testified before Congress multiple times on this issue, put it bluntly: we're building a more fragile civilization on top of an unstable planet orbiting a temperamental star. And we're hoping we get lucky. But here's something that keeps me up at night. Even if we had perfect detection and perfect deflection technology, there's still the human factor. Imagine NASA detects an asteroid with 80% probability of hitting Earth in 5 years. Not certain 80%. Do we spend $10 billion on a deflection mission for something that might miss us anyway? What if it's 50% probability? What if we launch a mission and deflect it, but then realize our calculations were slightly off, and we actually pushed it into a collision course when it would have missed? What if we deflect it away from New York, but accidentally deflect it toward Beijing instead? These aren't hypothetical philosophical questions. These are real decisions someone will have to make. And unlike in movies, there's no clear hero who makes the obvious right choice. There are committees, impact assessments, international negotiations, liability concerns, and political considerations. Dr. Kathy Plesko from Los Alamos National Laboratory worked on a simulation exercise in 2021 where NASA, FEMA, and international space agencies role-played their response to a hypothetical asteroid threat. The scenario: a 400-meter asteroid with 5% chance of hitting Earth in 14 years. Uncertainty region covering multiple countries. The result: chaos. Nobody could agree on who had authority to launch a deflection mission. Countries in the potential impact zone demanded immediate action. Countries outside the impact zone questioned why they should contribute funding. By the time the simulation ended, they'd spent 6 years arguing about governance and liability, while the hypothetical asteroid got closer. Plesko's conclusion: the technical problems of asteroid deflection are largely solved. The political and organizational problems are not, and those might actually be harder. So here we are. We have the technology to move asteroids. We proved it with DART. We have the ability to detect them. The Rubin Observatory will find thousands. We understand solar storms and how to protect against them. We know what needs to be done. And yet, we're still vulnerable, still unprepared, still hoping we get lucky one more time. But maybe, just maybe, the recent wake-up calls are finally getting through. The 2012 near-miss solar storm, the 2013 Chelyabinsk meteor that injured 500 people and cost $33 million in damages, the 2024 discovery of 3I/Atlas coming uncomfortably close. These aren't abstract threats anymore. They're real events that happen to real people in our lifetime. The question is, will we actually do something about it before the next one hits, or will we keep rolling the dice, betting on luck until our luck runs out, because make no mistake, it will run out eventually. The universe is patient, but probabilities always catch up in the end. So let's talk about what happens next, not in some distant future, but in your lifetime. Probably in the next few decades, maybe sooner. Here's the uncomfortable truth that planetary scientists don't usually say out loud at conferences. We're not asking if anymore. We're asking when and how bad. Dr. Amy Mainzer, principal investigator for NASA's Near-Earth Object Surveyor mission, said something in a 2023 interview that stuck with me. Every time I give a public talk, someone asks, what are the chances an asteroid will hit Earth in my lifetime? And I have to tell them 100%. Asteroids hit Earth constantly. The question isn't whether we'll get hit, it's whether we'll get hit by something large enough to matter. She's right. Earth gets hit by car-sized objects every few weeks, house-sized objects every few months, Chelyabinsk-scale objects every 60 to 100 years, Tunguska-scale events every 100 to 300 years. We're 116 years past Tunguska. We're not overdue yet, but we're well within the window, and the window's closing. Statistical models are great until they're not. Saying Tunguska events happen every 100 to 300 years is like saying the average person has one testicle and one ovary. Technically true in aggregate, meaningless for individuals. The universe doesn't space out impacts evenly. You could get 3 Tunguska events in a decade. They're nothing for 500 years. Or you could get one tomorrow. The Torino scale, that's the official scale for rating asteroid impact hazards, runs from 0 to 10. 0 means no hazard. 10 means certain collision with global catastrophe. We've never had anything rated above 4, and those all dropped to 0 after better observations refined the orbits. Sounds reassuring. Right, except the Chelyabinsk meteor would have been rated 0 on the Torino scale because we didn't know it existed until it hit us. The scale only works for objects we've detected. It's like having a fire alarm that only goes off for fires you've already noticed. Not particularly useful. But here's where things get weirdly optimistic. We're living through a genuine revolution in planetary defense. Not maybe someday technology actual. Operational systems coming online right now. The NEO Surveyor Space Telescope launches in 2027. Unlike ground-based telescopes that have to look through Earth's atmosphere and can't observe during daylight, NEO Surveyor operates in space using infrared sensors. It can detect asteroids by their heat signature. Even ones approaching from the sun's direction, that blind spot that got us with Chelyabinsk. NASA estimates it'll find 90% of all near-Earth asteroids larger than 140 meters within 5 years of operation. 90%. That's a game changer. That's the difference between hoping we get lucky and actually knowing what's out there. The Rubin Observatory, which we talked about earlier, will complement this by tracking everything that moves in optical wavelengths. Between these two systems, we'll have the most complete census of potentially hazardous objects in human history. By 2035, we'll know where almost everything dangerous is. And we'll have options. Real options. NASA's following up on the DART success with the NEO Surveyor mission to refine kinetic impactor techniques. The European Space Agency has HERA, which will study the aftermath of the DART impact in detail, helping us understand exactly how much force we need to deflect different types of asteroids. China's developing its own planetary defense program. Even private companies are getting involved. Asteroid mining ventures like Astroforge need to understand asteroid composition, which conveniently is also crucial for deflection planning, for the first time in the 5 billion year history of Earth. One species has the technology to see dangerous objects coming and actually do something about them. That's profound. Every dinosaur, every trilobite, every species that ever got wiped out by an impact had no choice. We have a choice. But asteroids are only half the threat. What about solar storms? This is where the news gets more complicated. We can't deflect solar storms, but we're getting much better at predicting them and hardening our systems against them. The Parker Solar Probe, launched in 2018, is literally flying through the sun's corona, the outermost part of the sun's atmosphere, studying magnetic field dynamics up close. It survived temperatures exceeding 500 degrees Fahrenheit and is sending back data that's revolutionizing our understanding of solar activity. Dr. Nicola Fox, director of NASA's Heliophysics Division, called it our first steps toward true space weather forecasting, like how we forecast hurricanes but for the sun. The Solar Orbiter, a joint ESA-NASA mission, is providing views of the sun's poles for the first time. Turns out, A lot of solar activity originates from polar regions we couldn't see before. Having eyes on the poles improves forecasting accuracy by maybe 30%. And the practical infrastructure changes are happening, slowly but surely. The Department of Energy released a plan in 2023 for grid resilience against geomagnetic disturbances. It's not fully funded yet, of course it's not fully funded, but at least there's a plan. Some utilities are voluntarily installing protection systems. It's not enough, not nearly enough, but it's more than we had a decade ago. The real shift, though, is philosophical. For most of human history, cosmic threats were acts of God unpredictable, unavoidable, outside human control. Now they're infrastructure problems, engineering challenges, things we can measure, model, and mitigate. That mindset change is huge. It means asteroid defense gets funded like hurricane preparedness or earthquake retrofitting. It means solar storm protection becomes a routine part of electrical grid design. It means we stop thinking of ourselves as helpless victims of cosmic chance and start thinking of ourselves as planetary stewards who have responsibilities. And this is a big, but all of that depends on sustained attention and funding. And humans are really bad at sustained attention for threats that haven't killed anyone recently. We're currently riding a wave of concern driven by recent events, the 2012 near miss, the 2013 Chelyabinsk impact, the successful DART mission, the discovery of 3I/Atlas. Funding is flowing. Programs are being developed. People are paying attention. How long does that last? 10 years, 20. What happens when we go another 50 years without a major impact? Does funding dry up? Do we dismantle the detection networks because nothing's happening? Do politicians campaign on cutting wasteful space programs that haven't prevented any disasters lately? Dr. Gerhard Drollshagen, who worked on ESA's Space Situational Awareness program, has seen this cycle before. After the 2013 Chelyabinsk event, everyone wanted to fund asteroid detection. We had meetings, proposals, commitments. 5 years later, half the funding disappeared because the crisis had passed. But the crisis didn't pass. We just stopped getting hit for a while. Those are not the same thing. This is the challenge. Preventing disasters means the disasters don't happen, which means people don't see the threat, which means they question why we're spending money on prevention. It's the ultimate paradox of disaster preparedness. But let me tell you what keeps me optimistic. The kids who watched the DART Impact livestream in 2022. Millions of students around the world watched humanity deliberately change the trajectory of an asteroid for the first time in history. They saw that science fiction became science fact. Some of those kids are going to become the engineers and scientists who develop the next generation of planetary defense systems. We're raising the first generation of humans who grew up knowing that asteroid defense is a real thing we can do, not just a movie plot. That matters. Cultural shifts happen slowly, but they do happen, and technology keeps improving. Machine learning algorithms now detect asteroids in telescope data automatically, finding objects human astronomers miss. The James Webb Space Telescope, designed for deep space observation, occasionally spots near-Earth objects as bonus discoveries. Even amateur astronomers with backyard telescopes contribute to detection networks. Remember, Gennady Borisov discovered an interstellar comet from Crimea with homemade equipment. The detection network is becoming democratized. More eyes, more sensors, more data. Each year, the invisible becomes visible. For solar storms, we're developing better forecasting models and faster warning systems. The goal is to push warning times from 17 hours to maybe 24 or even 36 hours. Every extra hour of warning time means utilities can take more protective measures. Airlines can reroute more flights. satellite operators can safeguard more spacecraft, and individuals can prepare too. Because here's something nobody talks about: personal preparedness for cosmic threats isn't that different from preparedness for any other disaster. If a Carrington-level solar storm hit tomorrow with 24 hours warning, what would you do? Well, withdraw some cash. ATMs will stop working when power fails. Fill your bathtub with water. Municipal pumps need electricity. Charge all your devices. Buy non-perishable food. Fill your car's gas tank while pumps still work. Basically, the same things you do before a major hurricane, except this hurricane could last weeks or months. The difference is awareness. Most people have hurricane kits or earthquake supplies if they live in vulnerable areas. How many people have solar storm kits? How many even think about it? But awareness is growing. After the 2024 solar eclipse, when millions of Americans looked up at the sky and remembered we live on a planet orbiting a star, interest in space weather spiked. Google searches for solar storm preparedness increased 300%. Maybe people are starting to connect the dots. And that's really what this whole story is about: connecting dots. 3 I/Atlas passing through our cosmic neighborhood. The Tunguska explosion that demonstrated what even a small asteroid can do. The Carrington event that showed us the sun can be just as dangerous as any space rock. These aren't separate stories. They're chapters in the same book, the story of Earth's relationship with the cosmos. For billions of years, that relationship was one-sided. The universe did whatever it wanted, and life on Earth just had to deal with it. Most species didn't deal with it very well. 99.9% of all species that ever existed are extinct, and a non-trivial number of those extinctions involve things falling from space or the sun having a bad day. But now, for the first time, one species can fight back. Not with anger or violence. You can't punch an asteroid or yell at a solar storm, but with knowledge, preparation, and technology. We can see threats coming. We can move asteroids. We can harden our infrastructure. We can survive. The question is, will we? Will we sustain the effort? Will we fund the programs? Will we make the cultural and political changes needed to treat planetary defense as seriously as we treat military defense? I don't know. Honestly, I don't. Humanity has a mixed track record on long-term thinking and collective action. Climate change should have been solved decades ago, and we're still arguing about it. Nuclear proliferation should terrify us more than it does. We're really good at ignoring slow-moving threats until they become immediate crises. But cosmic threats have one advantage. They're not political. An asteroid doesn't care if you're liberal or conservative, American or Chinese, rich or poor. A solar storm doesn't check your voting record before frying your power grid. These are genuinely universal threats that require genuinely international cooperation. And maybe, just maybe, that's what finally brings us together. Not through fear, but through the recognition that we're all on this fragile blue marble together. And the universe occasionally reminds us of that fact in dramatic ways. The next Tunguska event is coming. Maybe in 50 years, maybe in 200, maybe next month. We don't know. The next Carrington-level solar storm is coming. Could be 2025. Could be 2089. The next interstellar visitor like 3 I/Atlas is coming. Might be a harmless comet. Might be something worse. But here's what I do know for the first time in Earth history. We'll see it coming. We'll have options. We'll have a fighting chance. And sometimes, in a universe that's mostly empty space, crushing gravity, and deadly radiation, a fighting chance is all you can ask for. So the next time you look up at the night sky, and I really hope you do, because it is beautiful and humbling and worth your time, remember that darkness isn't empty. It's full of rocks moving at cosmic speeds, stars that occasionally burp plasma in our direction, and objects from other solar systems passing through on trajectories shaped by forces we barely understand. But also remember, We're watching. We're learning. We're preparing. And when the universe next decides to tap us on the shoulder, we're going to be ready. Or at least, we'd better be.